In part 2 of the CoreSpecViewer demonstration, we're going to look at some of the spectral interpretation and analysis features, and we're going to work on an existing CoreSpecViewer native dataset. So this is a file that I've processed using CoreSpecViewer. It's from a hole drilled by the Geological Survey of Ireland in County Roscommon. As you can see, for this hole I've already produced the segments and the masking has been done. So with the process data, we have the same functionality where you can double click on a pixel to see the reflectance data of that pixel. In this case it's been smoothed because we're looking at the South Goal cache dataset. But we can also right click to see the continuum removed spectra. This can be quite useful if we want to look at some of the variation in the features. But to get an overall idea of the spectral variation in our dataset, we can use the Quick Cluster button. This uses a k-means implementation, and we're just going to use the default values of 5 clusters for 50 iterations. If you're working on your own data, you'll have more geological knowledge of the data, and you can use that to refine the k value, the number of clusters, to get more meaningful results. The iterations do take a little bit of time. As you can see, we're on 35, but we've finished before 50 with 0 pixels reassigned. And this will produce 2 product data sets in our cache data collection. The image shows us here the spatial variation of our clusters. You can see that class 3 is dominant. It's mostly in this grey kind of area on our false colour image. Class 4 and class 2 seem to fill in on these white areas, so that's obviously significantly different to class 3. And then we have class 0, which seems to be localised to a few small regions in the far left run. But to find out what these clusters mean spectrally as well as spatially, we can actually interrogate the cluster centres. So here we have our different classes, the number of pixels each class contains, and if we double click on class 3, this is the cluster centroid of that particular class. We can see this nice feature around 2308. If we were to look at class 4, we can see it's a significantly different spectral shape. It doesn't have this 2300 deep feature, it has a broader absorption. They both have something going on around 1900 or some water feature. And if we look at class 0, we can see that we do have a 2300 feature. It's shallower than our feature in class 3, and we have another feature around 2200. So anybody who knows anything about the geology of Ireland will not be surprised to learn that this is a carbonate, or anyone who's familiar with hyperspectral data won't be surprised to see this 2300 feature in limestones. So if we want to look at the particulars of the 2300 feature in more detail, we can do it quickly and coarsely using the band maths. So this is a module plugin for CoreSpecViewer that allows you to just type in expressions or individual bands to look at that data. So what we can do is we can just define the 2300 feature, and we will just display the reflectance at 2300 nanometers on reflectance spectra, not on normalized spectra. And that will then become a cached product. And as you can see, where you don't really have a 2300 feature, you have much higher values for reflectance. Not surprising. If we wanted to look at an approximation of a feature extraction, we can actually type a formula into the band math option. So we will go for 2300 depth band maths, and we can type an expression R2300, and we can divide it by an interpolation between the reflectance at 2200 and the reflectance at 2400, and we'll perform this on reflectance spectra, not on normalized spectra. Okay, so I put a typo in there. This demonstrates that actually the bandmath module is quite robust to typos. It won't crash your whole system. We can demonstrate it again. We'll call this R2300 interp bandmaths, and we want the reflectance at 2300 divided by an interpolation with no typos between the reflectance at 2200 and the reflectance at 2400, again on reflectance spectra. And there we can see it's almost the inverse of the... It's very similar to the 2300 feature because it is recording depth, but there's a lot more detail in there now. And we also noted in one of the classes a feature at 2200, so we can use the clay index, a well-defined one, to look at that 2200 feature. And we'll just call it clay index. You can see it's almost the inverse of the 2300 nanometer feature that we extracted using the band maths. If we wanted to look in more detail to try and calculate the true position of the 2300 feature, we have a number of predefined features. These are mostly lifted from the Laukamp et al. Paper 2021. The full references in the documentation and in the code base of this feature. We'll have a look at 2320. This uses the feature extraction implementation from Highlight, and it's set to use a polynomial fit. You can adjust the settings in the code base to use a quadratic fit or a full Gaussian fit. So here we can see that this calculated the depth and the position of the feature. If we have a look at the position, we can see that the carbonate mineralogy is consistent throughout this hole. Throughout this box, there's very little variation. It's all around 2317, 2318. And if we look at the depth, we can see that's also quite consistent, although we have shallower depths in the regions in the last run, which was consistent with this class 0, which had both a 2300 and a 2200 nanometer feature. To do any further interpretation, we would like to use library spectra, exemplars of existing minerals. CoreSpecViewer comes with the EcoStress database. It comes preloaded, although you can add custom databases. So we know there are some carbonates in here. Let's look at the calcite. If you double click on a library entry, you can see the spectra, and if you right click on a library entry, you can see the continuum removed spectra for that library entry. We can see from looking at these spectras that our libraries cover a variety of different band ranges, and we want to make sure that we're using an exemplar that does completely cover our dataset. So we can use this filter to current band range, and this will take the spectral range in our existing data and remove any spectra from the library that are not. It will add spectra from the library into this in-range custom collection that cover the full band range. So let's do a correlation of one of these spectra against our dataset, and this will just produce an image of correlation coefficients of our data against calcite. So you can see where we had that class 3 and that nice carbonate feature, we're getting 0.7, 0.7, low 0.8 against calcite, and if we were to run the same correlation against dolomite, you can see we're getting 0.8s and 0.9s. So we do have carbonates, and they are most likely dolomites based on this correlation. And these are cached, these images. They will be saved to disk and can be reopened. We can also open a custom database. So this is a database I created earlier. These are minerals that are likely to be in our core based on my knowledge of the geology, although I don't think biotite is. So we can actually add these to a custom collection, and I will call it reasonable. And we can now perform mineral mapping against our custom collection. We have a number of options. We can perform straight Pearson correlation. We can use a spectral angle mapper, and we can use the modified spectral angle mapper. We can also check Pearson against multi-ranges using winner takes all, although this has several drawbacks, used with care. Or we can select a particular band range to perform correlation against. For this demonstration, we'll just use the Pearson collection, the Pearson correlation against our reasonable collection. So it will produce a mineral map, Pearson mineral map, reasonable correlation. So we can see we have dolomite where we expected to find dolomite, and we also have these vermiculite horizons. They may or may not be vermiculite, they may just be clay minerals or white micas of some kind. And we're identifying chlorite in here, although I don't know that that's too likely. This may just be fitting on noise. We can also go back to our k-means clusters and match those against our reasonable collection. As you can see, it's not happy with the majority of them. They're mixtures, I would say, which is why it's not assigning a mineral to them. And it's happy that class 3 is dolomite, as we suspected. If we had a very unusual mineral, we could actually just use these library building features, and we can add a spectra from our image. For example, here we can just click a single spectra and we can call this unknown 1, and we can add that to our library, or we can add a regional average. So we can select this area here, and this will add our region to the library. If we look in our library, then we have this new collection, user defined. These are the minerals that we've added: unknown region, unknown spectral 1, and it's added in the box and hole number and the pixel or region coordinates that we've used. And if we wanted, we could actually run a mineral map using just our selected regions. So again, we'll do Mason, we'll do it on user defined, and you can see we have our user defined mineral map, and yeah, it's just highlighting all of the consistent areas that we saw. So that's some of the tools available for box level interpretation and persistence to disk of all of these datasets. But as geologists, we're rarely interested in the details of a single box. We want to be working at the hole level, what's going on in the full hole. So that will be what I show in part 3 of this demonstration.